I'm going to talk about some of the same things, but from a more of an experimental point of view, from observations that we've collected in 2 field experiments that I've been involved with. One is called DYNAMO, which you're probably mostly aware of, which is, let's see, it's to study the genesis to some degree and propagation mechanisms of the Manikandan oscillation along the equator, here south of India at 80 degrees east. And then the second is PISTON, which Eric has given a really great introduction to, which is good because I don't give a very good introduction here. So that was off in the Western Pacific up the Palau Ridge. So I'm going to be talking about a number of phenomena, and I'm going to sort of hang them on the observational analysis that I've been focused on from these experiments. So I'll talk about intraseasonal variability and tropical cyclones and monsoon tails, and the real way that these affect the air-sea interaction is, for the most part, through their wind stress. Eric talked about how the sea surface temperature can affect the atmosphere, and I'm actually going to talk a bit about that in my tutorial, but today I'm kind of talk about it the other way, the atmosphere affecting the ocean, or a bit of both. And so these affect the ocean through wind bursts primarily. When there's not wind, interesting things happen to the ocean and the atmosphere. We get diurnal warming, which you're aware of. We see this, I think you've seen this in mesobob as well, and in Assyri. They're sort of a universal phenomenon. Don't happen all the time, but so you get diurnal warm layers when the wind is calm and the sun shines down on the ocean. And they have effects on the boundary layer atmosphere we're starting to see as well. And then cumulus clouds are coupled to the atmospheric mixed layer, boundary layer, and cold pools are a mechanism that also have a strong influence on the surface temperature and recharge the surface boundary layer with dry, let's see, a little bit dry, but especially cold. They're cold air. So the observations I'll show is surface fluxes, turbulent. We measured turbulent and radiative fluxes, mostly on ships. That's what I'll show. We also have atmospheric soundings. I'll show some atmospheric soundings from the PISTON experiment. And I'll show some atmospheric turbulence measured in the surface mixed layer in stratiform rain, which we can measure from radar and from clouds. So here's a schematic view, and this is actually meant to represent a wind burst event and all the sorts of phenomena that happen in that event in DYNAMO, based on the observations from DYNAMO. And so let's see, time actually propagates to the left, and this is so that longitude for the Manikandan oscillation or Kelvin waves, atmospheric Kelvin waves, would propagate from the west to the east, can both be resolved together here. So you can see that here before the strong convective event, here's the strong convective event, and it's attended by wind bursts. Before it, it's sunny and relatively calm. So there's the solar radiation. These wedges here are warming, diurnal warming of the ocean. The ocean also has a salinity maximum in it along the equator. And so that entrainment later will entrain warm water before it entrains colder water. And so we have this these warm layers which become weaker as convection and wind increases and convection becomes stronger, also blocking the sunlight. And then in the second MJO that was observed in DYNAMO, there were 2 distinct wind bursts, probably associated with atmospheric equatorial Kelvin waves. And we see in the soundings that they had warm anomalies aloft, and they had these tilted wind structures which fit the description of convectively coupled Kelvin waves. And so when that happens, the ocean, there's lots of turbulence observed in the ocean, mixed layer deepens, and eventually cold water, at first warm water, but eventually cold water is entrained into the mixed layer. And then later, the sea surface temperature is allowed to warm up again. And it does so in these diurnal things that eventually get mixed down. Okay, now this is observations of time series from PISTON, and sort of Eric has shown some of these in different ways. So in blue is the zonal wind, and so you can see the effect of when there's an eastward zonal wind associated with extension of the monsoon or monsoon tails into the Western Pacific. So the monsoon is coming farther out into the Pacific off the Asian landmass. And these are often associated with large-scale atmospheric conditions which foster tropical cyclones. Here's tropical cyclone Jebi, which Eric showed a nice spatial example of in his plots. And here's the sea surface temperature and air temperature. The sea surface temperature is the almost always warmer, and which is typical of the tropics. And you can see when the wind stress is weak, you get these little spikes in sea surface temperature. These are diurnal warmings. And in contrast, when the wind stress is stronger, here and here, you get you can even have here's kind of weak, but you can have mean cooling of the sea surface temperature. And also you get very disturbed atmospheric conditions where you frequently have cold pools that are 2 to 5 degrees, 2 to 4 degrees, I guess, and colder air temperature. And we, because of the wind stress, and also because of to some degree, because of the cooler air temperature, we have stronger latent and sensible heat fluxes associated with these tropical cyclone / monsoon tail wind events. And here we also have rainfall associated with them. And rainfall is a very spotty field unless you average a lot, and we didn't average a lot because these are observations from a single point on a ship. But nevertheless, we see that these tails and tropical cyclones that were they're actually quite far away from the ship. We were in a position where we were in no actual danger, luckily, and also by plan and design of the experiment. But nevertheless, the winds associated with the synoptic configuration led to these sort of large mesoscale convective clusters, actually even synoptic sort of tails of the monsoon that dipped down over our ship. Even though we weren't in the cyclones, we were experiencing related weather. So here I zoom in on Jebi and Kongray, and here's an example of a typhoon. We don't have the reanalysis data yet from 2018, but here's an example from Typhoon Noru in 2017, and here are just a couple of days, a couple of days of propagation. You can see that there's this monsoon tail, which is more or less in the same sort of large-scale synoptic vortical structure, but it isn't the deep tropical cyclone itself. Okay, so we had an opportunity, the moving around arrows here, the black one is the ship. We had an opportunity to use the Palau soundings and the Yap Island soundings to make a sounding array, so we can actually compute divergences when they made a nicely shaped triangle for our operation. So we can compute the gradients of the winds, the temperature, and the humidity, and do budgets for a polygon, a triangle in this case, of these 3 stations. And there's this method by Yanai, Esbenson, and Chu where we calculate the apparent heat source using dry static energy. This is S is the dry static energy, which is like the moist static energy, but without the latent heating. And then we compute the moisture sink, and these are in, let's see, in dynamic units of watts per meter squared. And these are largely responsive. So these are the averages over the cruise. There's a hiatus here where we're in port in Palau, and when we get too close to Palau, this triangle becomes highly, what's the right word? Scaling. It becomes very skinny and not a good way of measuring. We can only measure gradients in one direction, so it doesn't work very well. So we blank those out. So the moisture sink, which is the important term in the larger term in the moist static energy budget, is largely driven by convergence in the atmosphere, which drives deep synoptic rising pressure perturbation, rising vertical velocity. So when the pressure velocity is negative, the vertical velocity is up, indicated by these arrows. And these times are also the times when you would expect precipitation, rising and cooling of the air and precipitation. And in fact, the precipitation is leaving a net heating in the atmosphere. It is acting to heat the atmosphere and make it rise, doing that work. And so this is the radar, the precipitating area from the sea pole radar that we had on the ship. And you can see that when there's strong these synoptic rising events are associated with stronger rain. And actually the rain, if you look closely, the rain is actually lagging the rain. This is the rain area. The rain area actually lags the upward motion somewhat because the rain area, the larger area rain is by stratiform rain systems which follow the convective rain. The stratiform rain being hydrometeors that are change into ice phase and then eventually settle out and become rain and fall down over the region. So I'm going to talk next about turbulence observations in this stratiform rain. And so we had a upward looking cloud radar which measures, for our purposes here, it's a Doppler radar, but it also measures reflectivity. And we can characterize the modes of the falling stuff into a mode of ice, which has a very small vertical velocity, and rain, which falls at about 4 meters per second, with some variance around that. And then far to the left, where the reflectivity is very low, this is mostly clouds. Okay, so I'll show some examples of Kelvin-Helmholtz billows where the stratiform rain falls through, and as the air blows the hydrometeors up and down, we can then measure the air velocities from the perturbations that the air induces on it. And I'll give another example of entrainment at the base of cirrus cloud. So here's an example of a Kelvin-Helmholtz instability that we observed, or billows that we observed in DYNAMO. And so here's what it looked like. This is a stratiform rain that's falling at a uniform 4 meters per second, except it has these oscillations on it from these billows. And I just zoomed the color scale in on them. And you can see that there's actually this very large, probably a breaking eddy because it has large Doppler width, and that means that the vertical velocity that's actually observed in the individual radar volumes has high variance. And then as another example, often the base of clouds looks kind of flat, but in this case it's actually sort of punctuated by all these little upward and downward velocities. And these, you might call them eddies at the base of the cloud. And this is a bit above the freezing level. And so I've recently worked up an analysis on this. So I'm going to just look at, I'm going to zoom this whole thing down into this spot. And so here's a longer time series of, let's see, 14 hours or 12 hours or something. And this is dissipation computed in from the spectra of Doppler vertical velocities of the hydrometeors. And here there's rain falling all the way to the ground, so we can calculate that from the radar. And here is like I showed here, where the cloud, there's a cirrus cloud, but there's no reflectivity down here, so we can't calculate the dissipation. But this is the region, this is the spot that I just showed a picture of right here, and you can see there's this strong dissipation at the base of the cloud. We also see that there's mixed layers at the base of the cloud. These are the potential temperature sounding. So there's, it looks like there's evidence of mixing going on, and then a strong, an inversion or a strong density gradient above that mixing. And they're also associated with strong wind and strong wind shear at the base of the cloud. So we have having this continually running remote sensing and Doppler velocities gives us, we can occasionally catch, or often catch, really interesting things, and we can occasionally figure out what it is that we're seeing. Also, you can see in this picture there's about a 300 to 500 meter mixed layer at the surface when the rain reaches all the way down to the surface. And let's see. I'm going to zoom in on, okay, can't remember what's next. Yes, so I'm actually going to look at the time there. Notice here, there's times of diurnal warming, but I'm going to switch gears to the DYNAMO cruise when we had a LIDAR, which measured the surface boundary layer, a subcloud mixed layer of the atmosphere very well. And this is a time period which also has diurnal warm layers. So there's a much too thin red line here that I'm tracing, which shows diurnal warm layers. You might be able to see the base of the solar radiation. So the red line follows the solar radiation, which warms the ocean temperature up. And interestingly, here we can see that the colors are the dissipation from the Doppler LIDAR, and you can see that the dissipation, the mixed layer deepens and the mixing strengthens when the sea surface temperature warms up due to increased buoyancy flux from the surface. And a bit of in Piston, I also noticed that there's these slight diurnal cycles that when the sea surface temperature warms up. This is a cruise long average, so sometimes we don't have strong diurnal warm layers. Those are also averaged in here. So even so, there's a couple of tenths of a degree temperature anomaly in the afternoon. And interestingly, it's coupled, I didn't necessarily expect this, it's coupled through a deep sort of 3 kilometer shallow cumulus layer. And these clouds are usually not raining, but they're sort of intermittent, but it's interesting that those clouds are coupling the surface temperature quite deep into the atmosphere. And finally, I'm going to talk about cold pools. Here's an example from the radar when it was there was stratiform rain and a cold pool came barreling through. It came in this direction, and you can see there's almost a laminar raising up of the air, upward vertical velocities in front of the cold pool, and then turbulence behind it. And it also spawns some funny little, this turbulence spawns some funny little clouds behind it as well. And cold pools in the temperature time series look like this, with a strong depression of temperature and then a slower recovery. And this cold pool, is like almost a half a day cold pool, but they're sort of fractal. If you look in at this structure here, it has lots of quick, you zoom in on it, there's lots of quick temperature drops and slower recoveries. So I have a paper about the cold pools from DYNAMO, but this is a cold pool from DYNAMO, but this is the same time series from Piston that I showed before. And this is from DYNAMO. This is the same picture from DYNAMO, and exactly what I showed before, except there's these times when the mixing is quickly shut off. And these are actually corresponding to cold pools. And if we look at the wind structure also, there's actually the shear, the strong wind shear, which starts at the surface and kind of rises up as they mix out. These cold pools are inducing strong wind shear, and they're also very stratified, so they're actually stopping the turbulence, which is briefly stopping the turbulence which is generated by the surface buoyancy flux. So I think that's sort of fun to observe. So first of all, wind from tropical cyclones, monsoon tails, and Kelvin waves are enhancing the surface stress and the heat flux and evaporation flux and buoyancy flux in both the ocean and atmosphere. It's interesting to note, though, that the buoyancy flux is discontinuous across the interface because some of the heat fluxes are carried by radiation, which is not absorbed. It is absorbed in the ocean and not in the atmosphere, and also because the virtual temperature flux, which is the difference in density between water vapor and air, is an important, at these high temperatures, is an important part of the atmospheric buoyancy flux, but it isn't, and it's proportional in some sense to the salinity flux in the ocean, which is a buoyancy flux, but it isn't the same at all. The proportionalities are determined by different physical coefficients or different state, because the ocean and the atmosphere obviously have different equations of state. And the wind maintains mixing in the upper ocean. In calm periods, the few surface meters of the ocean warm up under sunlight, and the warm sea surface temperature enhances buoyancy flux into the atmosphere, and that warms up the subcloud boundary layer and even couples with the shallow cumulus clouds over a depth of 3 kilometers. And the ocean mixes the warming down at night, so it's sort of the mixing in the ocean is out of phase with the mixing in the atmosphere. We have mixing into the atmosphere during the day due to positive buoyancy fluxes and positive buoyancy fluxes into the ocean at night. And so we actually remotely sense this turbulence in the atmosphere, and I didn't show it, but our collaborator, well, Emily and other collaborators observed the fluxes in observed the turbulence in the ocean at the same time. And so we can also observe the shear and the turbulent kinetic energy and its dissipation. The diurnal atmospheric surface mixed layer are observed when there's weak winds and diurnal warm layers in the ocean. And I mentioned already that the ocean and atmosphere have opposite diurnal cycles of mixing and stratification. And the cold pools additionally stratify the surface layer for very, very quickly and very briefly for maybe an hour or a few hours. And they enhance shear and suppress turbulence. And I'll also show in my tutorial later that the cold pools cool and dry the subcloud mixed layer. They're an important part of that mixed layer heat budget. All right, thank you for your attention.
So we have time for a few questions.
Coupling between the surface temperature and the 3 kilometers high in the atmosphere, I think James Rupert and others have argued that that's important for moistening with the MJO and eastward propagation. Do you think that that also can help moisten to the north of the Boyle summer ISO envelope? And has anybody looked at that yet?
I haven't really looked at it, but I wouldn't be surprised. Yeah, I think that there are also contours in there that showed moistening going along with the temperature anomaly. So it's not. I think that's not surprising. And this was in piston, so it's not particularly at ISO at all, let alone MJO region. So I think that's probably going on all the time.
Questions? Hyode.
So I see the very strong cold pool events and heat flux reaching hundreds of watts per square meter, but there's no SST changes in your plots. It was
in the cold pools.
Yeah, but the mixed layer
they're very short. The cold pools are not very long lived, and so
yeah, but
there may be a case where there's a strong wind that does cause an SST variation, but you have to remember that also the cold pools are only a few 100 or maybe 400 meters deep at the most. Okay, maybe some of the deeper ones, some of the bigger, longer lasting ones may be deeper.
So,
But I think that it takes a while to cool off the SST.
yeah,
That's my
I
feeling.
was expecting that SST would respond to that short-lived heat flux event.
Well, there is a strong, they do enhance the heat fluxes,
Yeah.
but they only do so for a brief time and not long enough to get much mixing or entrainment at the base of the ocean mix layer.
All right, so let's thank Simon again.